Thank you. Thank you for organizing this. Thank you for the presentation. Okay, so this is the first time I'm showing this project that I've been working on for a while now. It's, you know, it's an itch that, you know, I had, and I started scratching it. Of course, you know, now that it's almost usable, I have to also start thinking about what is it good for? You know, what is it other than providing me an endless source of fun? It's been my experience that in reality, for us software developers, or for me personally, users are a very important component. So it's they not just give you, satisfy your ego that somebody is using you, but they also push you forward with their reasonable or unreasonable requests. And that was one of my first experiences as a software developer, where I worked with somebody who kept changing requirements on me, and after a while, after going through a few stages of frustration, and but look, I did what you asked for. Here it is. It's working. And but it turned out inevitably that every time I implemented a new set of requirements, I ended up with a better product. Something else had also changed. It was faster, better, smaller, better organized. So, I started to not just be less frustrated, but to really appreciate the feedback that people can give you on, on your work, on your creation. So now, of course, it's even better if it happens that your work is something that pays your bills, because then you can live in this endless blissful cycle. But this is to say that I'm looking forward to hopefully have also some users, and they will push me forward better, more than I would have done it myself. So what this project is, it's not a replacement for the existing Smalltalk VM. So you will see from a few figures, because I did some measurements, of course, and you will see that this is in no way competitive yet. But no, in reality, it's not competitive with Smalltalk VM as far as performance goes. But what I do hope it is, and there are many ways in which the platform is inferior to Smalltalk, as a playground where you can experiment and understand about the system, and play with the underlying implementation, and implement a better ordered collection or a better. So this is not that playground, but hopefully it will be able to run most, if not all, your significant projects that you have in Smalltalk. And if you want to see them run on the web in a browser, so that would be so it's a platform where you can extend the reach of your own software pieces, and of course it goes through a process, a deployment process. It goes through compilation, which is lengthy. So there's no way the near instantaneous cycle of development like in Smalltalk. you pay a price. You spend time compiling it, pushing it. But after that, in the idea that you have a reasonably large program, that hopefully pays off by the widespread usage of the browser. So let me start sharing my screen. And let's start with a Smalltalk view of the world. So I've been a heavy user of the test runner and the test suite that comes with Squeak. And yeah, we can bitch about some of the tests. There are a few bad apples. There are a few tests that do some stupid things, or hard code some things unnecessarily. But the vast majority of them are actually very useful, and they do manage to cover a significant part of the the Smalltalk code base. And as such, they proved invaluable to get things right for many of the things. I would give special mention to I believe it was probably Nicolas Sellier who added a lot of boundary conditions to numeric tests and floats, and all those. Yeah, there's a lot of work that went into these tests, and from my point of view, it really paid off, because yeah, you have to get right all these primitives that one has to implement if you rebuild the system from scratch. So yes, essentially, I had to rewrite all the primitives by hand. But other than the primitives, other than the, I should say, the core primitives, the ones that are part of the VM, those were implemented by hand. But the ones that are part of the plugins, they are also generated code. So the work, the compilation work has essentially two major steps. One is you compile, you use a VM Maker like approach. Well, it is using VM Maker, and I started with Vanessa Freudenberg's version of the VM Maker that she used for SqueakJS. And of course, I had to modify it pretty heavily, because one thing that since this is compiled Java code, JavaScript code, sorry, and you have there is no stack machine. There is no stack interpreter. So because of that, that's what the VM Maker generates with pushes and pops of the stack and so on. So I had to modify it even more than Vanessa did for SqueakJS, which is still a stack-based interpreter. So in my case, but it worked. So now I'm generating the plugins as well. But as I said, that's a separate compilation step, and this is the little workspace script that I run to generate the plugins, and this is this is so. For example, you don't need not everybody who would want to have their image exported to JavaScript would have to load VMmaker and regenerate the plugin. So that can be done once per VM, essentially, and then. But for the image side, you still need to run essentially the other two major steps that are left for the image, which is one, exporting the code, all the classes and all the methods, exporting them, transforming them to JavaScript and exporting them as JavaScript files. And then a second step, also exporting the state of the image as essentially a huge storeString, a JavaScript source string that is then read on the JavaScript side. So there is no essentially image binary image reader, or because there is nobody on the JavaScript side that is prepared to do all these code transformations and compilations to generate JavaScript out of the existing compiled methods or classes that are in the image. So the compilation is only done from the Smalltalk image side, and it's in the form of files, and that's what gets loaded by JavaScript. And this is essentially what the JavaScript word looks like once you generate it. So as I mentioned, there are the plugins which you did once, and then they stay there unchanged for a long time. But then there are also the classes. So, well, the classes are files here in a folder, and of course we also generate a JavaScript module to load them all. And this is all generated code, but it's generated code that allows them to be loaded a little bit in parallel as well, and to be loaded while also respecting the class hierarchy. So it ensures that you don't try to load a subclass before it's superclass. And we also have a similar, much smaller class for the map types. So these are this is JavaScript code that gets added to the JavaScript primitive type, well, equivalent to primitive types, the object wrappers of the primitive types in JavaScript. So because obviously, you cannot make them inherit from you cannot insert them for the map types. You cannot insert them in the existing Smalltalk hierarchy. So then what we do is we export all the methods that exist in the hierarchy for those types, descended from object down, essentially from proto object down. So they all get added to the prototypes of these base types. And let's take a look at what the mappings look like. So essentially, we have the primitive types. Now, for example, this image that we're looking at well, we'll be looking at shortly. It's a 4 or 5 image, but where, for example, character and float are not immediate types, but we know that they are coming. So in later versions, and they do naturally map to primitive types in JavaScript. So therefore, they are mapped. So, character maps to a primitive 1 character JavaScript string. But of course, for characters, we have the small complication that in Smalltalk, we did some bit fiddling there, and the characters, in addition to their code point value, if we look at them as Unicode characters, we add some in the upper bits, we add some leading car bits. So they are more than just the Unicode character that they represent. And because of that, we have to take care. So that's why we have essentially a dual mapping. So the normal characters, the ones that don't have a leading car, they do map to the primitive string, 1 character string in JavaScript. But the ones that do have a leading car, they mapped on the JavaScript side in the class character that is exported as well. So there we have an actual character object. So it's not an immediate anymore. So it's a character object, which does have a value instance variable like it does in Smalltalk here, Smalltalk 4.5. And that value contains as well, not just the Unicode code point, but the leading car portion as well. Now, of course, true and false are mapped to a Boolean. These are straightforward. We have another fun mapping for floats. So floats, and with integers, small integers as well, because we only have 1 primitive type for numbers in JavaScript, and we have more candidates on the Smalltalk side. So on the Smalltalk side, we take small integers that are in the range of JavaScript safe integers, which is 2 at power 53 minus 1, essentially plus and minus. So that's the range of sort of immediate small integers in JavaScript. So if by default, if a JavaScript primitive number is integer and is in the range of integers, then it's the mapping of a Smalltalk integer. So all the rest are floats. That's by default. So these are the 2 mappings that I refer to, and the discrimination is done based on this condition, if it's safe integer or not. Of course, it becomes a bit more complicated, because what do we do with the floats that are actually integer values but are still floats? And for correctness purposes, we still need, if you send, if you try to do a division of the number, the float number 1.0 with 2 versus the integer 1 divided by 2. So it's the same message with the same argument, only the receiver varies, and the receiver has to determine what the result will be, whether this will be a fraction or it will be a float result. So we need a representation of integer floats. So because of that, I created on the JavaScript side a class float, which is a subclass of number, and which also implements value of, just like the normal wrappers for numbers. So, JavaScript does do some boxing and unboxing automatically, and it does have essentially object wrappers around the primitive types. So the float that we created, we implemented on JavaScript side, behaves very much like the existing number wrapper for numbers. So, the value of method, whether it's sent automatically by the system or we sent it explicitly, so it will return the number primitive. And, this essentially this this class is used in our when we export the image state from Smalltalk. If it's a float literal, that is an integer number, so that will be created explicitly as this kind of wrapper object to ensure that we have a float and not an integer. And also, the primitive that says, if you have a small integer as float, that one also returns a float wrapper around that integer value. So this is how it's possible to have both small integers and floats be mapped to the primitive type number. But in addition to that, we have a third class for floats, and this is needed because sometimes there are in Smalltalk we construct a float from bytes. So we need this kind of construct, and this is similar to what Smalltalk does with large large integers. So although large integers map naturally to the now available begin in JavaScript, we also have the issue that sometimes in Smalltalk we create large integers from bytes, and so we still need the large positive integer class and negative integer in JavaScript for these particular situations where we create an empty large positive integers and we start populating its bytes, and eventually we use that value. So again, like with the other number wrappers, so these again, they behave like wrappers for the numbers. Even begin can have a wrapper, and so they all implement the value of, and the value of for the large integer classes, the return begin. And again, for begin, we have a discriminator to see, because in the JavaScript code, when we send the message class to an object, we still to recover the correct original class. And this is how we recover the class, for begins, based on the fact that if it's larger than 0, then its class will be a large positive integer. So for primitive types, the class of the primitive type is not its constructor like it is for all the other objects, but it is the originating Smalltalk class, equivalent of the Smalltalk class. And another primitive mapping is for block closures. And block closures, they map to the primitive type function. So that way we can have literal blocks, just like we have function expressions in JavaScript. So they map very naturally. And again, just like in the case of numbers, we also have the class block closure for the situations where we construct a block closure for non-literal blocks. So but all the other classes normally have their their class is their constructor, and of course not one of we have of course a bootstrap class, which is the one that's used for essentially creating the original the bootstrap for the meta class hierarchy, and so all the Smalltalk classes are mapped to JavaScript classes, which is very nice, and of course the methods live, of course, not the real JavaScript methods live on the prototype, not on the class itself, but okay, well, so let's show a real class, not the bootstrap classes for now, so to illustrate. So this is a normal class, and all the classes are essentially namespaced in this Smalltalk global on the JavaScript side, and they start with an underscore so that we can easily recognize them and distinguish them from JavaScript classes types, and so we use normal class creation constructs in JavaScript, and we also generate some. So, for example, for the instance size, we know on the Smalltalk size. What that is, I'm sorry, this is unclear, but so this is the instance size for the instances of this class. Here we have a static initializer that allows us to essentially, construct the reflective part and the meta class for the class. So we say that we take the superclass from JavaScript, and we tell it to initialize the constructor for this, and we pass the format of the class, the format of the meta class, the category, all the simple attributes that don't require any object graph relationship. So the ones that are numbers or strings or so on, we pass them in this initializer method for the class, and these are the ins var names. So it's similar to the method that selector that is constructs classes, or displays the definition of a class in Smalltalk, and also at the end. So this function is part of the initializer. So this is for the meta class, and we can see what this does a little bit. We go. This method exists in class, and this is for all the root classes initialization. So all the root classes, while the class itself inherits from nil, so its class side inherits from class. So this is where we set that prototype, and this is where we we construct the structure that corresponds to the Smalltalk classes and meta classes, and of course, we have to briefly also talk about the object format. So the object format, of course, other than the map type, the object format is similar. Well, it's very similar to the one that SqueakJS uses. So essentially, we have for objects that have pointers, we have a pointers array. It's a JavaScript array, and this is how one looks like. That's automatically filled with nil, and for byte classes, of course, we have a byte array, well, a JavaScript uint8 array actually, and for word subclasses, variable classes, we have instead of we have a words property for the object, which is a uint32 array. So with this, you know, a generation time, you know, we know which classes have pointers and which don't, and which have, and also based on this, now in Smalltalk we have just related to this object structure, we have you know, the same primitive for various kinds of objects. So you know, it's if we go here to class a proto object. So these primitives, you know, they exist essentially. Their implementation sort of exists on all the classes, but they actually do something different depending on if the class is variable or not, if the class is a byte variable class, if it's a word variable class, and so on, if it's a pointer variable class. So because of that, you know, at export time in Smalltalk, we know all that about the class. So we generate these implementation methods for the primitives, which will be used. So essentially, they override each other. So you know, at runtime for each class, the appropriate primitive 60 implementation will be called, and that happens in the normal in the actual primitive code, which for these special primitives that are overridden and that behave differently depending on the object format. So there, the primitive definition is, of course, aware of this, so it has a special format. So let's take a look at primitives. Now, primitives, these are not methods. A better name for the primitives would be, these are inlineable primitive bodies, because we don't have actually, these are not real methods. These are incorrect JavaScript. So they are just a fragment. It's just the body of a method. It's essentially a piece of code that can be inlined in the surrounding method. And that's how the primitives actually get there, because at generation time, the code on the Smalltalk side reads these snippets of code and inserts them in the method, in the primitive methods themselves. So these are essentially inlined in the primitive methods at generation time. And of course, they would be followed in a real method. They would be followed by the you know, primitive failure code. And I was talking about these special primitives that have varying implementations. So they take this special format. So we call the implementation of the primitive, and that we return it in an array with a test saying if it failed or not, and with the result. Of course, the result is only meaningful if the primitive succeeded. So and that's what these primitives do. So then this is the snippet of code that gets inserted in the method that uses primitive 60. So if the implementation succeeds, then this does an early return of the result. And if not, it continues with the primitive failure code. Now, before we start looking at the Smalltalk side, I've talked for a while. So if you have questions, you can, or if you prefer, I don't know, we can leave them further. But I'm afraid I don't want to go too far ahead if there are, things that I didn't explain properly. Okay, so let's continue then. So now on the Smalltalk side of the world, because after all, this is a Smalltalk meeting. So now we get to how all this magic happens. So this is the workhorse, the initiator of all things. And one of the first things that we do is we transpile all to JavaScript, because so when we do export, so this is the thing that exports everything, code, class definitions, and methods to JavaScript. And first, it exports the bootstrap class definitions. Here, because I didn't, for now, I don't support traits. I mean, traits, conceptually, I think they would be pretty easy to be implemented in JavaScript, considering all the rest that I already did. And it's simple to play with prototypes and add methods to them and so on. But in reality, I didn't, I did not see a lot of usage of traits, and they don't have good tool support. They don't have, so I didn't think it was worth the effort to support them. Of course, if some users show some real and valuable use cases, I mean, I think this can be relatively easily done. But okay, so I don't generate traits, and so I unload the traits before do. And this is the method that I showed that puts all the classes in hierarchy order and loads them all as much as possible in parallel. And then we export the actual code. This is transpile all to JavaScript. And we go through all the classes, and we take the method nodes and we transform them to JavaScript. Now, the first thing we do, we prepare it. So in reality, we cannot just traverse the existing method node and spill out JavaScript as is. JavaScript has differences. You know, in Smalltalk, everything is an expression. The Boolean constructs, if true, if false, and so on, they are expressions. And so there are semantic differences that don't match, because in JavaScript they are not. So therefore we have to transform the methods before we can just export them. Just replace the syntax with JavaScript. And this is what the method JsPrepare does. And of course, after we prepare it, then we call generate because, and that's another quirk in Smalltalk, that in reality the method node does not it changes structure while being generated. So some of the classes get transformed. The optimized selectors, they all get transformed, and so there are some transformations applied on the which change actually the structure, change the method node itself while being generated. So because of that, I am invoking generate because I want to go over the transformed, already transformed method node, and I prepare some properties that will be used during generation, and then we do the final walk through the method nodes and print them out as JavaScript. Now, okay, so now let's look first at prepare, and the first thing we do is normalize, and this although I had some code for doing transformations for a long time, but this has gone through many iterations, and as you see, I kept them for now. These I kept. Every time I get something that broke my assumptions and something didn't work, I kept putting these as comments in the method. Of course, after a while, I dropped it. So, but initially, that's how I was making progress. So, every time I got something funky, a method that had something else, then I would put it as a test case here, and and then I would fix it. Okay, so now this starts with some weird preparation, because this normalization, these code transformations, they have a goal. So they and because we call them, maybe I should have done 2 different methods, but I was lazy, and so as I already mentioned, there are 2 major code generation steps. One is for the plugins, and one is for the normal Smalltalk code. Well, in the plugins case, the situation is different, because many of those methods, they they want to be inlined. So there is an inlining mechanism that exists for the plugins. And because it's as we will see, we'll go a little bit through the invocation mechanism that we use in JavaScript, and because that one is slow and it's a bit painful, so we have to try to compensate as much as possible. So one sure way to improve performance is to try to get the most that you can out of the primitives. So of course, with the handwritten primitives, the core primitives, that's okay. You code them as well as you can, and that's it. Now with the plugins, this is again generated code. So here in this case, we want to generate as good code as possible, which is a slightly different problem. And so here, we also look at which methods the plugin code indicates that they want to inline them and so on. And in addition to them, I think all the short methods and stuff, we try to inline as much as possible. So in addition to ones that were explicitly marked as inline by the VM plugin VM maker code, we also add all the short methods and stuff. So this is one of the goals of the transformations. So for the methods that are for the plugin code, these methods want to be inlined. Well, a method that wants to be inlined shouldn't look the same as a method that doesn't want to be inlined. I mean that there are certain transformations that you want to do for a method that needs to be inlined. You want to reduce the number of returns and so on. So you try to make it look weird. It doesn't look nice. You try to have one big return for a lot of nested if true statements. Not if true expressions, and this would not look good as your normal transform JavaScript code. And because of that, I'm trying to do this detection and see which are candidate for inlining and which not. Then based on this decision, we do slightly different. The heuristic is slightly a bit different for the steps involved in the transformations. So now going to the actual transformations, so this does what it says, and what it means is we are in JavaScript functions, although it's weird because it's not methods, but normal functions, if they have a name, the name of the function is accessible inside the function itself. So you can use it for recursive invocations and so on. So, but anyway, so the function object is available is in the context of the method itself, so you can refer to it there. And that was, I think, a precious thing that I wanted to keep, and because of that, also I don't use the normal way of constructing a class with methods in JavaScript. So as you see here, the class declaration ends very quickly. All the methods are not added directly to the JavaScript. You can, so there is a syntax for declaring, in addition to structure, so you can declare some fields or methods, but if you declare them as methods, the methods don't have this nice property that I was just mentioning, and they cannot refer to themselves by name. So they lose that property. They do have a name, but they cannot refer to it inside the method. So because of that, after I create the class, I add the methods to the prototype through object assign instead of declaring the methods directly inside the class body. So and this way, you know. So that's why, because we want to have the name of the method available inside, you know. If any temp were to clash with it, we rename it. Of course, we remove cascades, which don't exist in JavaScript. Then we do a step for removing non-local returns. This is an optimization, and you know, we are trying, because as I said, our method invocations are painful. We'll get to them immediately, and we try to avoid both method invocation as well as full closures as much as possible. So we do some transformations to get rid of them. And in particular, so there's two major transformations here that we do. And one is for if missing block. You know, the constructs you have at if absent, or the various you know, or detect if none, and so on. And in many of these cases, you know, you can see in the if absent or in the if none block. So for the missing case, you have a non-local return. Now that non-local return that transforms, of course, the block in a full closure, and of course we can generate, we do generate non-local returns. That's not a problem. But if we can avoid both the closure generation and the non-local return code generation, you know, we'd rather do it. So that's what we're doing here. So essentially, you know, the idea is that we replace the return, instead of throwing instead of an explicit return in the if missing block, we replace the return with a local return for the block, which is a special literal you know, called missing marker. And that will be you know, of course in the case of all these methods, that is the return value of the whole, you know, at if absent or detect if none. That's the return value of ends up being the return value of the message. And then on the other side, we are adding a check for if the result is this missing marker or not, and that is a simple if expression. And if we see that it's true, then we add a then we add an explicit return, but that is outside this closure. It's inside the method itself. I will show you an example. And similarly, I'm trying to eliminate non-local returns from exception handling blocks from undo methods. And then, of course, we want to normalize if true, if false, because you know, we do many transformations based on special selectors. We want to minimize a little bit the cases. So we remove if false, we remove if true, because we don't want to check for them. So everything will remain just as if true, if false, and we don't need to remove if false, if true, because this is done already by the the macro transformation during generation that I was mentioning before. Similarly with if nil, if not nil, and so on. So some of these are done already by the Smalltalk compiler when generating the code. But we are doing the ones that are not done. So if false, if true, if nil. And of course, here, so another case that, for example, doesn't translate to JavaScript as is, for example, short-circuited Boolean expression where you have an and in Smalltalk you have a block there. Well, that block is not a simple expression because it can be a sequence of statements, of course, and you cannot put that inside a JavaScript short-circuiting AND operator, and because of that we have to transform these ANDs, and and some of them, of course, end up being just normal if true, if false statements. They cannot stay as ANDs. But after we do that, we also try to recover a Boolean expression. So to recover what's possible among the if true, if false cases, which some of them may have been in the original code written like that. The ones that can be transformed into AND or expression, we transform them so that we have in JavaScript it will be more advantageous if we can have these Boolean operators instead of if true statements. So, and here again, this is what I mentioned, because we remove the complex and or complex or. Now here, we need to treat specially the optimized blocks in Smalltalk, because the ones that are part of if true, if false, or there are the to-do loops and so on. So there are certain expressions in Smalltalk that they are in reality optimized, and the blocks are not real blocks. And we want to, but because they also, even though they are optimized, they also may appear in situations where they are treated as expression, value returning expressions. So we have to be careful with them and during our transformation. So we mark them. This is again for the array braces expression. We have to because of course JavaScript also has an array where you can put objects in an array, a literal array expression where you can put objects, but if they have to be expressions, every value. So again, so these are the transformations for the transforming into statements the expressions that are not. And we also we also take special care of case of, because JavaScript of course has has a switch statement, so we can use that, and it's also an optimized case. So instead of keeping blocks and using closures for case of, we transform them into optimized JavaScript constructs. And here, we for situations where an if true, if false expression, for example, which is an optimized expression, is the return value of a block. We have to we have to transform these expressions, to introduce additional temporary variables to hold certain values. So we create them for all these optimized blocks. Okay. And now let's look a little bit, because I kept referring to this, and it's an important part. And we can look at it in Smalltalk as well. So essentially, so other than various special cases that we do, so when we print out a selector, and for a normal selector that is not an optimized one, and what do we call an optimized selector? It's essentially the ones that are not message sent in Smalltalk, like class equal or not equal. So those are, we treat them as optimized selectors in JavaScript as well. So we won't invoke them in the usual manner. But other than these three, essentially, all the other ones are called via a yield expression, and it's a yield iterator. So because all our methods are generated as generator functions, and this is done in order to achieve green threads in JavaScript. So of course, JavaScript is not threaded, and we want to we don't really care about true threads, but we do want to keep the Smalltalk semantics of processes as green threads, and the way we implement that is by using so all the invocations are yield invocations on generator functions. And with this, essentially all the process switches can be done via a simple yield expression, a normal yield expression. And where are those yields used? Well, they are done inside the special process switching primitives that we have in Smalltalk. And so if we now look at the Smalltalk in JavaScript, so every method, in addition to being a generator function, every method has inserted, the VM creeps in, so has inserted a preemption point at the beginning and inside loops as well, just like Smalltalk does. So now this becomes visible in the source code, which, it's not so nice, but for now I haven't found a way to hide it, but maybe I can, play a little bit with source maps. Anyway, so the idea is we have an activation counter. When it reaches 0, then we do an interrupt check. And there, if the things are, it may happen that if there's a semaphore or other kind of situation, let's go and look at that. So essentially, this is just a wrapper for this is the real function. So we check if this is for a user interrupt. We check if there's a user interrupt. And this, essentially, we signal the various semaphores that are. And again, for now, something. Sorry, I skipped a step. So here, so until this moment, so this is a generator function, and we still call this method again as if we wanted to traverse it through a normal yield construct. But this particular function, instead of continuing to iterate through the message chain, this one here actually does a next. So this one stops going down the message chain, and this one just calls this real interrupt, and where we only have semaphore signals, which may or may not yield. So and that's why we call this next, and we will get back a value. And if all the semaphores yield with a real value, with a string usually saying the reason for preemption and if any of the semaphores yielded, so we want a process switch, then we yield it. So this is this is one of the very few places in the code that does an actual yield of a value. So this is a moment where actually there would be probably a process switch, and this happens inside it's here, sorry. This is essentially the scheduler loop. So it's very very easy. So here we are at the bottom of the stack, and we just every process essentially is a generator. So that's the equivalent of a suspended context. So because this is this would be the place in the process where the suspended context would be, and but we, of course, we don't have real context, so but we just keep there the generator, and we invoke next on it. This is at the bottom of the world. And whenever somebody yields, we get back here. And now, in addition to the normal yield from a semaphore that wants to switch a process, sometimes we just have this, a request for relinquishing the processor for. There's a primitive for that where you say for how much you want to release it, and this is how that's implemented. And this, this sets a timeout for the set timeout. This is a continuous loop of set timeout invoked recursively. And of course, if the value yielded says quitting, then it means we want to get out. So this is where it stops. But if not, normally we go back and we take again the Smalltalk, the active process, and we invoke its next on its generator. We invoke the next method again. So this is how we resume processing another thread, and we can take a look at the the semaphore signals. Actually, yeah. So here, and this is how it looks like with the inline primitive that I was mentioning. This is in reality the body of primitive 85, which is here, but and here, we check the priorities and we see who's next in line. Once we got a process that's supposed to be the next active process, we set the Smalltalk VM active process to the new value, and that's when we yield. And at this point, we get back down here to the bottom of the loop, and since there's a new active process, that will be the current one, and then its generator will be invoked next time. And this is how the magic of process switching happens. But okay, so as we were talking, so this is about process switching. In addition to process switching, this, as you can see, it says check interrupts or exception. So it does not only check for interrupts and potentially looking at semaphores and potentially process switching. In addition to that, this allows for, while we are not the active process, we are parked, this allows for somebody else to throw an exception on our generator, which can happen. So there is, Smalltalk has this capability, of course, using contexts. So we also we use this generator throw mechanism in JavaScript to achieve the same thing, and this is where it would happen. So if this we just yielded, so right now we are parked. So after we come back, so once we are resumed, then we check if we have an exception attached to our process, and if we do, then we return it. But that means that it will be returned here, and it means that we now signal the exception. So in reality, the exception will be signaled, and it will be signaled in the right place, because our generator is where the Smalltalk equivalent context would be, and this is exactly where we signal this exception. But except we signal it when the process is actually active again, which I think has some benefits, because it's very hard to simulate the correct behavior for a non-active process when you throw an exception inside. This brings us to the other sort of important aspect about exception handling. And yeah, let's see what's happening when we signal an exception. So, here, this is some special casing for test failures, because, they are important when you're trying to get the system right, but ignore that. In reality, so this is where the magic happens. So all the processes have attached an exception handlers chain to them, and when we signal an exception, we walk the chain of exception handler for the active process. We check who can handle it, and then we invoke the handle on that handle. And of course, if we don't find anybody, it means the exception is unhandled. We do some more logging, but essentially this is what Smalltalk does as well for a non-handled exception. We invoke a handle signal on nil. And we have one class that I added, which is the Smalltalk exception handler. And which gets this, of course, the code generation inserts these for undo expressions. And maybe. Yeah. So so this is an undo expression. So as I mentioned, this would be a literal block. We also give it a name because it's handier if we see some names in the stack and so on. So we makes life a little easier when debugging. But essentially, this would be a literal block, and in addition to creating a function expression for it. We also set some Smalltalk block kind of values on it. We set the receiver, the start PC, the number of copied values, and the compile method. And as you can see, now where do we find the compile method? Since we don't want to do an expensive lookup for the actual reified Smalltalk compile method, this is where we use the function name. So all the functions. So this is ourselves. So we use our own function, and we take the compiled method from our own function. So this is how we get the current compiled method. And this is so compiled method and their equivalent. So this is the Smalltalk, the JavaScript representation of the Smalltalk compile method, and they have a bidirectional pointer with the JavaScript functions that they represent. So both the function holds the compile method, and compile method holds the function. And so we can easily get the compile method, and then we call the undo, and this is the undo block again has a block literal, and again we set its instvar so that it can be treated as a real block in case somebody uses the block instead of just calling value. They treat it as a real block and do something with it, or they log something with it. So and that's how the functions do get, they are a map type, so they do get all the methods from a block. So with this, we give them a chance to also respond to most messages sent to a block. Now, there are many things, but I just, I want to show also some late additions that I added to sort of bridge the world between Smalltalk and JavaScript a little better. So I added, and here we are on the Smalltalk side, and I added here, in addition to the various options that we have already for decompile, bytecodes, or source, I added JavaScript. So here you can see the JavaScript source for that would be or will be generated for this method, and of course I mentioned the using the function itself to get to reflect reflective properties, and this is our function name, and here we refer to it, and we are taking the literals from it, because the function, in addition to pointing to the compile method, this is a minor optimization, but instead of going through the compile method and getting the literals, I also put the literals directly, and this is not a Smalltalk array. This is actually a JavaScript array, of the contents of the literals that belong to that compile method. So this is a JavaScript array containing the literals of the compiled method equivalent to our current method. And this way, we have access inside the method to literals. And the reason we do this is because if we don't have literals, of course, we would need to instantiate JavaScript objects equivalent to strings, for example, or we would need to create byte strings out of the primitive string and so on. So we would need to do all kinds of things here. We would do a lot of object creation, and here we can just use the literals and refer to them, and we refer to the same literals that already exist. And here, of course, we create some constants for the literals that are actually used within this method, and specifically, we check if some of the literals are used within blocks or within loops. So then we create a special constant for them. Otherwise, we just use literals, and this is only for literals that are used multiple times or are used inside the loop or are used inside the block. Other literals would be just used as this inside the code. So that's just another minor optimization. And of course, the same thing now can be done in the equivalent method that we have. So now we're finally to take a look. Come on. Now let me see. Actually, sorry. Somehow they didn't like moving them to another screen. Let me. Let me share my other screen. I think it's easier. Okay, where am I? How do I get back to this? Sorry. Can you see my other screen? I don't know.
Yes, we are seeing your other screen now.
Oh, okay. All right. Thanks. All right. So here we are actually in the browser, the same image as exported. So And one thing here to note is that you know, as a small hack that I did recently, I added this JavaScript inspector, and of course, that tries to bridge the world between JavaScript and Smalltalk. And of course, this cannot be just Smalltalk code in order to bridge the world. So I need to find a way to embed some JavaScript code inside Smalltalk. And you know, for now, the way I did this, I just put a comment that starts with JS and ends with JS tag, and this will be at JavaScript generation time. This will be embedded as is JavaScript in addition to the rest of the code, which is translated JavaScript. So here, if we look at JavaScript, now here's the try block there, which of course it's not a comment anymore, so it's real code. So this way, you know, the Smalltalk method continues to behave the same way, but when it gets to JavaScript, it has this. And now, of course, there's an additional problem because I don't really have, you know, in the exported image, I don't have the sources normally. So for normal methods, all we see is decompiled code. And if we look, you know, at the decompiled code, but the way normally, because this is just a comment, this would be gone in a decompiled code, and because of that, I had to add another hack on top of the hack, which, you know, I modified the parser to recognize these special comments, and if it recognizes a method that has these special comments, it adds the source of the method to the properties. So therefore, the generated methods will have in its properties, it will have the source for sure. And this is how now on the JavaScript side, although when we the methods shown normally are just decompiled, but it will keep these comments because it will show the source as the original source. So and now, in addition to seeing the source, so now this is an inspector. So, you know, we can just say here we use a normal inspector initially. Let's say, okay, so this is a browser on the JS inspector class. So of course I inspect itself, so which is just the class of JS inspector. But now we also have this inspect underlying JavaScript representation. And here we have the same JavaScript class, but this time it's viewed as JavaScript. So this is a primitive function in JavaScript. And you know, because it's a class, it also has pointers, which are where we store our metadata. And it has a constructor. Of course, it has the class side method open on with. It also has, I store here the binding for the class. And again, for ease of going from, to the reflective parts of the system, I treat bindings a little bit specially. But now, for example, okay, so the pointers are an array, so I can even ask it, okay, inspect underlying, and this is an array, but this is not a Smalltalk array. It's actually a JavaScript array, and it has at slot 0 it has the superclass, at slot 2 the method dictionary, the format, and so on. So, and of course, and in addition to this, we also have the capability of not just doing, of course, we can do Smalltalk evaluation. Smalltalk evaluation works normally, just like Smalltalk evaluation should work, whether it's an inspector or not. But here we can also do a JS inspect. And now, now this is brand new code, so maybe I was over ambitious with it. I don't know, 2 + 2. Yeah. So the thing, what I wanted to show is, I don't know what the other one didn't work, but so this evaluates the code not as because we are using these special menu items. We are not using Smalltalk evaluation. This is using JavaScript evaluation. And because of that, this is not, it does not use completion semantics. So, you can, whatever you put here will be the body of a method. So that's what you have to think about. It will be a body of a method in JavaScript. So we are creating a function around this snippet of code that you put here, and we are creating a function based on that, and that's what we are evaluating. So that's what you have to keep in mind. So if you just put 2 and 2, well, yes, it can maybe create a function with that, but it won't return it because there is no return in that function. So it would be a method, a void method. So you have to keep in mind if you want to do JavaScript evaluation. Now, of course, this is truly going without the net, because at this point, this is really in the twilight zone between Smalltalk and JavaScript, and things may very easily go wrong, and you can easily crash the VM with this. But it's a fun toy, and I hope to make it better. And of course, right now is just looking at the enumerable own instances, own properties of the JavaScript object that you're looking at. Of course, I can make it a more sophisticated JavaScript inspector, but for now, this is what I did. Oh, and before I turn it over to some questions, I mentioned before that before going there, I just want to show you one more thing with an additional kind of primitives, because I mentioned, I mentioned the overrider primitives, the normal core primitives. Now there are also the the named primitives from the plugins, and they are invoked a little bit especially. Are you seeing now my first screen, the screen with the JavaScript IDE?
Still on the second screen, I believe.
Okay.
Yes, that's got it.
Yeah. So So when we are calling one of these primitives, and this is also related to scheduling. So the primitives, we are less in control of what's inside the primitive code. And because of that, we have to be a bit more careful and cover more ground. And the primitives, in the plugins, they may invoke other functions, and they may, they don't always return nicely or in the same way. So sometimes there will be, a primitive failure exception thrown. So sometimes, so because we are not using the stack, as I mentioned, so I'm using, I throw a primitive return where one of these plugin primitives would return. But sometimes this is not enough, because sometimes some of the primitives use some asynchronous mechanism. So, for example, the file primitives, which I borrowed some of that implementation from Vanessa's SqueakJS. They use they use asynchronous calls, and similarly, for example, for clipboard handling, those are asynchronous calls. So you have to wait for them. So because of that, for those, I throw back something that signals that, hey, this was actually we succeeded. I mean, the primitive finished doing, but it just submitted an asynchronous call. So this wait for it to, because our call has to be essentially synchronous. So then we are waiting here in the loop, and we are waiting until the asynchronous call completed. In the meantime, relinquish the processor, and only after it finishes, then we return the value. And this is done in several places, but this is a way to bridge the gap between asynchronous and synchronous processing. And other than that, yes, I just briefly, we are talking. So this is still work in progress. So initially, I started working on, what was at the time current version. It was 5.3. But then I said I wanted to check, okay, what would be reasonable for me to achieve as backwards compatibility. And I said, I settled on version 4.5 because that one has closures, because I didn't really want to go beyond closures. I mean, of course, it would be possible, but I'm just one person. So because we don't look at bytecode. So from one point of view, we are a bit, this is source to source transformation. So for many things, we are a bit isolated from changes in the VM, but still, I mean, the closures was a pretty big deal. So other than that, of course, there will be some changes with Sista, but again, I mean, we already have the idea of inline-able primitives. So I think I didn't look very closely, but I expect that it will be relatively easy to implement. So it will be another change. So I suspect that I will have essentially 3 versions going forward, one for essentially 4.5, one for 5.3, and one for 6 with Sista, something like that. The code runs pretty well, but as I said, at least for now, all these generator and yield invocations, they take their toll. So this is not blazingly fast. I have some, comparative results. I was curious. So, I ran the test suite because the test suite does a lot and covers a lot. So currently, the current version, does compared to SqueakJS, it's very comparable. It has a bit more failures, but it ran a little bit faster. Of course, Elliot is in no danger. As you can see, the difference between 170 seconds and 4,000 seconds is quite large. And if you want to run it in debug mode, it's almost 3 times slower in debug mode than when you run it in run mode. But it's still quite usable. So for me, this has been a great adventure, and I just need to clean up the current chain set right now. I have I essentially what I have one change set, which is pretty big, that has a lot of changes spread, a lot of classes. So I plan to clean that up a little bit, and this will be the first thing I'll publish is essentially the current version targeting 4.5, and that should happen very soon, hopefully this week, and then following that, I will also want to publish something for 5.3, which should be pretty close as well, and then I'll also work on fixing the current failing test cases and so on. But I am pretty happy with the amount of coverage and the fact that it essentially runs almost everything. So this was a brief overview. So now I would be happy to answer your questions.
Thanks, Florin. So if anyone has got any questions, you can unmute yourself and just ask away, or otherwise just put them in the chat and we relay them.
Hi. Sorry, could I ask a question?
Of course, go ahead.
Yeah, so you haven't really shown this running. Have you tried using it as its own development environment?
Yes, you can write. Yes, you can change code. You can. Yes, I can show that. But yeah, essentially, yes, you can compile code. You can change code in the Smalltalk. I don't have a good story for sharing it back, so that's why I didn't really. But clearly, you can do both evaluations and class modifications, and you can change code and so on. It's not because I don't have a good story for sharing that back, so that's why it's not. I didn't emphasize that for now. And
so things like become and all instances and all that stuff.
Yeah, they work. Yes,
it all works.
Yes, become is implemented not by switching references, but instead it's switching bodies, it's switching the contents of the objects underneath. But yeah, but it works.
Cool.
And yes, and all instances are implemented. They are implemented as essentially through weak pointers. What I'm doing, and I'm pretty happy with how that works. So I'm using this JavaScript finalization registry. So essentially, each class has its own JavaScript array with weak references inside this map, and JavaScript has this notion of a finalization registry, where you are signaled when the object is garbage collected, and the cleanup is also called with a value. So therefore, whenever we add an object to our array with a weak reference, we register the element with its own index. So therefore, we get notified which index got collected right after JavaScript did it. So we can then, we know that that's a free element in our array, and that's how. So this allows us to not grow that thing too much, and we are reusing slots. So I'm pretty happy with how that works.
Cool, got it. Thanks.
Yeah. And this is the become code essentially.
Have you ever compared the memory footprint versus Squeak? I mean, running in a browser versus Squeak?
I
mean, how much memory does the image occupy in a JavaScript world?
Yes, it's several hundred megs. So yeah, it's not small. It's it's significantly larger, but not horrendous. So.
Okay.
So
Okay.
I have a question. So it's about, so with this, you translate the whole image, Squeak image, into JavaScript code.
Correct.
So, and you go through the method, the classes, the methods, everything. So, but what happens with the object, the other live object? So you have an image, but it's like
Yes.
It's not running, or how you, and also once you're on the JavaScript site, whether you can save the image in some way.
So the way we export the image itself, so yeah, it's essentially a storeString like approach. So here, when we export the image, essentially we, clean up as much as we can, and then essentially we Smalltalk globals just store on. So we store them as a string, and the resulting file, this is the serialized globals. Essentially, it's a 53 megs file that is essentially a JavaScript store string. I can.
But are you also serializing the state of execution of the image at that moment in time?
No. So that's so this is the image with all the objects. What we don't do, and thank you for asking. Yes. So no, the processes are nailed out when reading that serialized file, because yes, we are starting everything. We are starting the world from scratch. So what we are doing, essentially, once we start our scheduler loop, we clean up class delay, and then we essentially do what the image does when coming back up. We call delay startup, process scheduler startup, and then essentially the same. We run the whole. Then we run the whole process startup list, and then wake up top window, spawn new process. So this essentially starts all the processes, but they come up fresh from nothing. So it's not the old processes from the old image. So all the state comes without the running processes.
Okay, so you also had to look into the virtual machine code, obviously, to understand what was going behind the scenes, or?
Well, I had to do it, of course, in order to, but.
Yeah, thank you.
Yeah.
I would like to add. Actually, you mentioned that JavaScript doesn't have threads.
Yes.
If you would like, spend some more nights in debugging multi-threaded application, actually you can look into worker threads. Like I think Chrome and Firefox do support them. So it's ability to have some threads in JavaScript.
Yes, but Smalltalk anyway has essentially green threads. So for me, there's no advantage there because anyway, Smalltalk itself is not, it only runs cooperative green threads. So it does not run real threads. So that's why if it did, then I would have to look to real threads in JavaScript.
Okay, thank you.
Sure.
Hi, we have some questions on the chat. So I'm going from the top. There's Bill who's asking about when you were discussing process handling, you have a line that's got return yield star, and what is yield star doing in there? And then, you know, is also asking a few details about the coding style that you're using, so that I'm not going to repeat it, but if you can refer to the chat, you can see what it refers to.
Okay. Let's see.
That's a comment at 8:59 London time.
So yield star, what it does, so because all the functions, the original Smalltalk methods are mapped to generator functions in JavaScript instead of normal methods. So they don't call in the same way. A generator method, if you a generator function, when you call it, it just returns you a generator. Something that is prepared to listen to calls to next, 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 because it's moving from yield point to yield point. And this is something that normally, of course, you don't see in Smalltalk. Smalltalk also has preemption points, but they happen only in the VM. Here we surface them. They are visible essentially they are intermixed with the actual code. So you have a mixture of both VM code and original Smalltalk code. But the way the process switches happen, instead of happening behind the scenes like in Smalltalk inside the VM, they happen visibly here, and these happen through these yield. Whenever an actual yield without a star is encountered, that's when a process switch happens. So the code runs until it hits a yield expression. So, and the yield star means this is done recursively inside the chain of methods called. And I don't have any WebAssembly experiments for now.
Thank you. Sorry, I had to be away from my desk for a moment. Have we gone over the question from Dave about the performance relative to, say, SqueakJS?
I think I did, but if you wanted something more specific, I mean, I did show something towards the end, but I don't know that answer.
Sorry, I just had to go and have a, be away from my desk for a brief moment, so I might have missed it.
So do you have, like, I saw the fact that it ran the errors, all the errors, and you got the same results. And that's really cool. I was wondering about performance benchmarks or anything like that that you have in terms of.
Yes, but I think, so that's why I showed the time. So the whole test suite ran in JsSqueak in 4,000 seconds and in SqueakJS in 4,600 seconds. So
right. Sorry, I missed that.
It's a little bit faster, but it's comparable. So
well, that's one benchmark, but do you have like the tiny benchmarks numbers?
Yes, but I think this is much more realistic because and it also it runs enough code so that you know your real code will have a chance to run faster or slower with this. I didn't. Yes, we can run tiny benchmarks, but I don't think they are.
I just asked because the send performance is an oft compared number.
Yes, yeah. I'll publish those two. Yes.
And are you familiar with Pharo.js at all?
I'm sorry.
Are you familiar at all with Pharo.js, which does a somewhat similar thing, but a completely different thing at the same time? So we compile just an application, transpile it to JavaScript code rather than the whole image. I mean, it's an interesting thing you've done for sure. And right now we don't, for example, implement the full numeric stack, and we right now. So I got a whole bunch of ideas on how we could make Pharo.js's semantics be a lot closer to Smalltalk semantics, which I think would be great if it's not too expensive. But Pharo.js is more interested in sort of raw performance, so it runs quite a bit faster than SqueakJS, and also it's interested in interop with JavaScript libraries. So that was my other question. Do you have a story about interoperating with JavaScript libraries?
I don't have a story yet, so yes, it's yeah. This is. I mean, of course, interoperation is possible, but yeah, I didn't have time to delve too much into it.
What are your goals for JsSqueak?
Well, I want to publish it, listen to some feedback, fix the remaining test cases, make it a little bit faster, and then depending on if I get any feedback, if I get hopefully, it can run interesting applications. That would be the idea.
Thank you. So there's one final question, which is from Jay Ortiz about building an app compiled to JS and include just the runtime without the development environment. Is that something that would be possible?
But it is. I mean, in the browser, what I showed, it's there is no without which development environment, the Smalltalk one or the JavaScript one, because now we have multiple ones.
I would let someone else answer that, but my assumption would be without the Smalltalk environment.
Well, but then that's sure, but extracting an app in Smalltalk is non-trivial itself. So if somebody is able to extract an app, then I'm sure that yes, it would be possible to do it. And but that would be yeah, it would be interesting, but so obviously the exporting image needs to have all this all my code, all this compiler code there, so it can generate the necessary JavaScript. But it would need to have some additional support to identify the app, to generate that app. So that depends very much on the app that we are talking about. So sort of that would be your responsibility to define what is the app. once you export it, yeah, it's just a bunch of JavaScript files, and that's what gets loaded in the browser.